Yeah. We have a website with elections.
Oh, okay. Two left recording.
I found my chocolate milk made. Yeah. I was not lactose intolerant. It's like I want something fun to drink.
My sister works for Newman.
Oh, yeah. Hi, everyone, Newman.
Hello. Works for a company.
There's something I want to talk to you, but I forgot. Then I remember.
It'll come back sooner or later. Boy, we had that last night. We had this board meeting. Some president of the condo association.
Oh,
It's like,
no.
I needed like a hole in my head. There it is. And so it's been a difficult year for the building because it's starting to leak in various places. It's a 160-year-old building. It was never, when the developer developed it, he never really took care of the outside. And it's starting to, mortars crumbling and that sort of thing. So we are looking at really what is about a $750,000 repair of the building. So the board, last night was the owners meeting, and the question was how to get the, how to put this in front of all of the owners and deal with ultimately something that they're all going to have to pay for. So that was the essence of the meeting. And amazingly, they willingly and happily agreed to it by the end of the meeting. So it was amazing navigation, if you will.
Very persuasive.
Yeah, very subtle. I actually suggested not doing it.
Oh, wow.
I suggested a partial repair, which needs to be done. And their attitude was, look, let's get it done. But what was nice is that the board did not have to make the recommendation to spend all that money. We were the conservative element, and the owners came forward, and it just worked out the way I hoped it would work out. Running a meeting,
like reverse psychology.
Yeah, absolutely. Reverse psychology is running a meeting is so subtle. It really is its own art. It's a lot of fun. That one worked out, and I have all these emails just saying, good job, good job, good job, and I thought, wow. If I walked in and there told them that they needed to spend $750,000 to fix the building, I would have had an open revolt. I would have been relieved of my position on
That is why you're
getting, the art of getting to yes, right? My son is good at that. He used to work for IBM, and then he switched and he worked for a small company called Paladina, which is a healthcare, primary care pioneering company. And they were recently bought by a massive venture capital fund who wants them to grow tenfold over the next 5 years. And they're just infusing them with probably over $1 billion in capital. And my son is vice president for HR and has to hire all these people now. He's going to oversee an enormous expansion of the company, which was what he wanted.
Is that in Boston?
They're in Denver, is where they're based. They're all over the country, actually. Their model it's a different payment model. The employer pays for primary care, And that's it. It's a risk-based model, and they provide. You pick up the phone anytime you want and get a consult, or show up. It's different model of the world than the one that we live in. So they're the healthcare provider for the state of New Jersey right now. That's the kind of employer that they do. It's the state government or that sort of thing. When Matthew joined them, they were losing over $20 million a year, and in less than 3 years, they're now making about $5 million and on the way to making a lot of money.
That's awesome.
Yeah, Matthew doesn't fool around. Matthew had two characteristics when he was a kid that always told me he was going to go into HR and be successful at it. One was that he loves people. Matthew is a people person and wants everyone to enjoy their life. You only get to go around once. You should enjoy it. That's Matthew. So all the employees love him because he's dedicated to their happiness. The other characteristic which balances that is that he cannot stand inefficiency. It drives him nuts. And so when he sees inefficiency, he dives at it and makes it efficient. And so the corporate leadership loves him, and he gets away with both. It's just he has this thing where he does both at the same time.
My sister's also HR.
Yeah.
I think they're really good with him.
Yeah.
Is your wife coming tonight?
Oh, sure. Absolutely. Yeah, she likes the party. She does. No, I mean, she likes this party. She likes to party. Yes, that's also true. She oh yeah, no problem there. I don't think she's ever missed one.
Yeah, she's always.
Yeah, she's always there.
Oh, and we're recording. And it'll kill that.
Right. So what did Dilip say? Is Dilip coming? I know Zhao Young. Any minute he'll show up. And so screw him out. And Dilip is. I'll start in about 3 minutes or so. It was interesting. I don't know if Sri's still sitting there, but when I came in and he said, what are you doing? And I said, we're doing this. He says, oh, is that the series that starts with Bell's palsy? So I said, and he said, that really made a difference. He said, when before that series, I just sort of read the papers to see what they said. He said, but after that series, I knew how to read the paper. And I could really evaluate what the paper was saying, and it made a huge difference, which is what the course is about, is reading the literature. If we get into the late lectures, which at some point we will, I mean, we get into logistic regression and propensity analysis and all of the most advanced techniques. And they become really simple and understandable because it's constantly baby steps. So you're just learning one more thing each lecture.
It's falafel.
Oh.
There's falafel language.
Oh.
Dilip, good. Hey, Dilip. And I know Zhao Young is going to join us in a minute or two. I'll just wait 1 or 2 more minutes and then we'll get started. The other good part of these lectures is they're not dense, they're not packed, we can take our time and go through them. Some of the later ones are coupled to a second lecture where you pick up an article, a single article, and look at the article in detail. I don't know if we're going to do that or not. And then, like I said, there are some of the lectures are associated with these really great learning tools for calculations and that sort of thing. We never get into the math of anything. There's almost no math in this at all. Math isn't all that interesting anyway, truthfully, most of the time. What the math fundamentally does is it just looks at, it makes a prediction of what you expect. And then based on whatever parameters you want to put in, and then it looks at what actually was, and it just asks, is what you got what you expected, based on either accepting or rejecting the null hypothesis. I mean, it's really what it comes down to. And no matter how, and the math can get very complicated, but in the end, that's all that it is. It's just more complicated and more complicated versions of that single question.
Mhm.
All right, we'll start. Hopefully Jiayong will catch up real quick. So part two, what we're going to do today is, I actually left this in. These lectures, slide sets that I have were designed for faculty to use. The idea was that we would teach the teachers, and that's the way it was used actually. So I give it, but most of the time when we were giving this talk, we were giving it to faculty who were learning how to give the talk. So there were, after we had created the series, we then had a series of sessions where, faculty would sign up and learn to give the course. And some of them, like this particular one, have notes associated with it. So the faculty could, as they were reviewing, they could see what the point of each slide was. All right, this is for you now. These are our goals here. We're going to really build on yesterday's talk. We're going to enumerate and explain the various measures used to describe the frequency of exposure or disease, first of all, within a population, and then secondly, between a population. And when we talk about between population, we're going to use the term association, okay? And then we're going to just get into some of the nitty-gritty of terms that are very commonly used and very useful. We end with the number needed to treat or number needed to harm, which in many ways, I think, is the fundamental number. It is the most important number that you take away from an article because it is the number that you share with the patients when they ask why you're recommending something. And if you just think about what this revolution in stroke care on mechanical thrombectomy is about, the fact that your number needed to treat for mechanical thrombectomy is between 3 and 4, which is exceptional. That means for every 3 patients that you treat, you create 1 additional independent person, that's an amazing statement. That's colossal. I don't know of another treatment that has that kind of number needed to treat. At any rate, this is where we left off yesterday. This is the same table that we had, and so we're going to get into 2-by-2 tables. Is basically what we're going to do. Before we do that, we just want to make clear something that you probably know. This is almost certainly review for you, that we're talking about variables. Now, variables can be, in modern statistics, you can mix any kind of variable that you want. This talk about advances in math. This is only probably 10, 15 years old, that you could mix different types of variables into a single equation. This is a mixed effects model, which is really is a very important part of modern medical research. Hey, Jiayong, just starting. A continuous variable is a variable. So these can be outcome variables, by the way, or predictor variables. That's how I divide the world up. There are the predictor variables. Those are the ones that we input into the system. And then there are the outcome variables. Those are the ones, that's the reason that we're doing the experiment. We want to find out some result. That's the outcome. So variables can be outcome variables or predictor variables, either one. Variable types are the kind of value that you put in to the variable. All right. So sort of the prototype variable, if you will, is the continuous variable. So temperature is always a good example. Okay. It's continuous. You can measure, you could go, well, it's really 8 degrees, or it's 8.1 degrees, or it's 8.13 to go. You can go as far as you want. It's anything. It can take any value at all. That's a continuous variable. Okay. The next, I would say, is probably an ordinal variable. Now, we use ordinal scales all the time. The Rankin scale is an ordinal variable. The muscle grading scale, all right, the Medical Research Council's, is this 4 or 5 or 3, so that's an ordinal scale, okay? I mean, you can think of dozens of others. The EDSS is an ordinal scale. The NIH stroke scale is an ordinal scale. It only takes on discrete values. It's not allowed to, we use 3+, but it really doesn't have meaning within that. If you said, well, his strength is 3.1, I mean, that really wouldn't mean anything at all, okay? The difference between an ordinal variable and there's a couple of simple rules about ordinal variables. First of all, they have to be monotonically changing. You can't go up and down. If you start at 0 and you go to 6, then 6 either has to be better or it has to be worse than 0. 5 has to be worse or better than 6. You have to keep moving in the same direction. So, for instance, in the Rankin scale, because most people would rather be dead than 24-hour bedbound care, you nearly always, in order to use it, you have to link 5 and 6 together. Otherwise, it violates the basic assumption of an ordinal scale. And the other thing about an ordinal scale is that there's nothing interval about it. The difference between 4 and 5 is not 20% in the muscle grading scale, is it? The interval from 3 to 4, from 0 to 1, 1 to 2, those intervals are in no way equal to one another. Okay, that's okay. That's permitted for an ordinal scale. What has to happen though is that 3 has to be worse than 2. 4 has to be worse than 3, that sort of thing. It has to keep going in a monotonic direction. A dichotomous scale is easy. That's yes or no, up or down, black or white. I don't care what you want to call it. It's but it's independent or not independent, okay? Alive or dead, okay? So that's dichotomous. And a nominal scale is basically not, just like the name implies, it's simply a series of names. It has nothing to do with any direction or magnitude at all. Gender would be a good example, and race is probably the most common example of that kind of nominal. You divide them up into, white, Asian, Latino, non-white. That you just make these things up, okay? And man and woman is the same thing. You can do it by what part of the world they were in. This is, okay? Those are the variables. When we, at the level of the 2x2 table, before we start filling things in, we try to stay consistent in calling. Again, we have an exposure. They were or are not exposed. Exposed means typically it has to do with drug or surgery, okay? But it could be some other risk factor. They were in the vicinity of Agent Orange, okay, or not. Okay, so it can be any kind of exposure that you want. And then this is some kind of dichotomous outcome, good or got the disease, didn't get the disease, whatever you want. And then these are the obvious sums that come together. So these are all the people who were exposed. These are all the people who are not exposed. These are all the people who had a good outcome, just like we used yesterday. And that's your entire population. That was 319 yesterday. Now, when we start to talk about measures of frequency here, and this is measures of frequency within a single population. We're not talking about associations yet, okay? So there are several terms that may be familiar to you, but this, from now on, hopefully they mean something very specific to you. So the prevalence is the amount of disease which is already present in the population. It's a cross-sectional study, okay? You look at 100,000 people, and you find out how many of those 100,000 people right now on their problem list have a particular disease. That's prevalence. Risk, or what we're going to incidence, is a totally different matter. And this is much more complicated as a research tool. So risk is the likelihood or the probability, I like the term likelihood, but probability is okay, that an individual will contract the disease. All right, so that's the risk that someone, not who has it in the population right now, but the likelihood that an individual will contract the disease. Rate, which we're going to look at these in more detail in a minute, but rate is incidence divided by time. It is the speed with which a new occurrence of the disease occurs in a population. That's rate. And odds is a peculiar thing. Odds is a ratio of the probability of an event that the event will occur divided by the probability that the event will not occur. So we saw that as A over B, right? We're going to look at each of them in detail. Now, prevalence and incidence. So obviously they're related to one another, right? Because they both count in some sense the occurrence of a disease in a population. So what's the difference between them? It's the idea here of that this is the new ones that arise, and this is the one that are already present, right? So this is really helpful. So look at this. The incidence of ALS and multiple sclerosis are the same, okay? They're basically 2 per 100,000, all right? That's the incidence of the two. The risk of developing in the population, every 100,000 people, 2 ALS cases are going to arise. But the prevalence of ALS is 6, and the prevalence of MS is 100. So how do you get that? If they have the same incidence, why do you have such a higher prevalence of MS than ALS? Yeah, of course, ALS patients die, okay? Their life expectancy is 2 years or something like that. MS is 30 years or 40 years. So that's what's reflected here, okay? And that's the difference between incidence and prevalence. They're related. It has to do with the longevity. So let's look at, Michael's given us a bunch of papers here in this lecture to look at. So let's look at what he underlined or highlighted in yellow. So now, and to investigate the 10-year risk of dementia in subjects with mild cognitive impairment, we selected subjects, 2 different groups, then aging-associated cognitive decline or amnestic MCI, already diagnosed with one or the other, and then followed them. So subjects were reassessed. This is real. I'm surprised you didn't highlight this because this is important. The subjects were reassessed after 2, 5, and 10 years. So is this is the data that we're going to generate here prevalence or incidence? This is incidence. This is how you determine incidence, is you start with a patient population and you follow them. That's a lot of work. In case anyone's, that's a lot of work. Come back every 2 years. I'm following you for 10 years. And is going to get to the point of this, because what's the likelihood that one of these patients, age 40 to 85, is going to be able to complete a 10-year follow-up? So not everybody's going to complete that, right? You're going to have people leaving, you're going to have people dying, you're going to have people contracting diseases which remove them from the population. So this is a problem, that we're going to have to deal with in this lecture. All right, but then we can say that the 10-year risk of dementia was 0.28 in this group and 0.48 in the other group. Okay, and now we can, later on if we want, we can compare these numbers. But this is the incidence. This is the likelihood. So 0.48, a person reading it, the person with amnestic MCI has a nearly 50% likelihood of developing dementia in the next 10 years. Okay, that's what this is saying. All right, so the risk describes the probability of some event. It is a measure of the occurrence of new cases. It's quantified by measuring the frequency with which unaffected people develop the disease. So you start with people who don't have it, and you just follow them and see if they do get it. And that's a complex experiment to do. Risk is always between 0 and 1, all right? And it also requires that you determine a period of time, okay? So you can do it over the lifetime if you think you can follow a person over the lifetime, but that's not so easy to do, right? So you usually do it for a set period of time. And then this is the formal definition of risk. That is, it is the number of subjects who developed the disease within a given time period, divided by all of the subjects who you follow in that time period. All right. I'm going to look for the risk of blindness in any population that you want over the next 20, after they graduate from high school, whatever you want, right? But you have to define these, you define the period of time. The problem with risk, as we've been saying, is that it requires incident data. You cannot calculate risk if you don't do an incident experiment. Therefore, there are going to be times where we're not going to get to risk. It is necessary to follow them, and then you have this problem of the changing denominator. So let's look at that. We deal with the question of rate, all right? So rate, so let's look at this article. 207 MS patients were exposed to azathioprine, right? They wanted to follow them and see if they get malignancy. That's what this was. 5 malignancies were diagnosed in the azathioprine group, 7 in the control group. The age-adjusted occurrence rate was 3.62 per 100,000 person years. What the hell is a person year? Okay, all right. And in the treated group, and 4.24 per 1,000 person years in the non-treated group. Yeah. So right. Okay. So this paper is attempting to deal with the problem of people coming and going. All right. That's the issue. So rate is very close to incidence, but describes the speed with which the new cases develop. So risk was the likelihood that the new case would develop within a given time period. Rate is the speed with which those new cases develop. It's a measure of frequency, and it accommodates rate. Built into the calculation of rate is dealing with this problem of changing denominator. I'm going to show you how in a minute. The numerator is exactly the same as risk. The denominator is some measure of time, okay? So the denominator is a composite of the number of subjects followed and the duration of time over which each person was followed. So this slide is a really good slide, okay? So we're doing a very simple experiment. We only get 5 subjects enrolled, okay? We're just counting how long we follow each of these subjects. We're calculating the denominator for this experiment, okay? Subject 1 came in at the beginning of the study and stayed all the way to the end, 5 years. Subject 2 came in at the beginning of the study, but left the study after 3 years. Subject 3, so you can see it started in year 2, okay. So here, what you do is that you just add up the number, you multiply for each subject, you multiply how many years he was in the study. All right, and then you just add them together, and that's what's important, is you're just going to add these numbers together. So it's 5 plus 3 plus 4 plus 2 plus 3 is 17 years. And that is 17 person years. That's what a person year is, okay? You calculate for how many subjects you have, and for each subject, they are weighted, if you will. You multiply by the number, by the length of time they were in the study, okay? Now, if I wanted to compare the results of this, so I get a rate from this experiment, and I get here, we get if 2 new cases develop, then the incidence rate is 2 per 17 person years. Well, what happens if I do an experiment which has 27 patient years or 1,006 patient years? How do I compare these 2 rates? Okay, I tell you that eight subjects develop the problem in 72 patient years. Is it the same or different than this? It's like, I have no idea. Okay, so like yesterday, we said you can transform a variable in any way that's useful to you. So what you do is you say, well, you know what, why don't we just do it per patient year? Or as the article did, per 1,000 patient years. And so we can we'll calculate it for our experiment, and they can do the same thing in their experiment, no matter how many patient years there were. You just calculate a rate as so many events per 1,000 patient years. Then I can compare the results of my experiment with the results of their experiment, and we can see if they're the same or different. So there you go. So this would be calculated as 0.11 per person year or 11 per 100 person year. That's what we're doing. So rate can assume virtually any value from 0 to infinity. It's never negative. It does not reflect the proportion of people who develop, but rather simply the speed with which they do it. And why doesn't it reflect the proportion? Because you only studied them for a certain period of time. Okay. The value assumes a rate depending on the unit of time. So here's a thought experiment for you. This is Michael at his best. If a chicken and a half lays an egg and a half in a day and a half, what's the rate at which a chicken lays eggs in this experiment? So don't shout it out, but raise your hand or just indicate to me when you're done so that when you've made up your mind. How about that? Just as, everybody. So you all ready? All right. What's the answer?
1.
All right. So the number of eggs represents the number of cases. So that's 1.5. The person time at risk is 1.5 chickens laying eggs over 1.5 days is 2.25. So the rate at which eggs is laid is 1.5 divided by 2.25, which is 0.67. Okay? All right. All right, odds. Let's move on to odds. A population-based patient registry to identify first-time ever idiopathic neuropathy in people receiving statin. So this is called this is an interesting design. This is called a nested case control. So we haven't got into case control, but I want to introduce this term of nested. Okay, so we're starting with people who take statins. So we're only interested in people who take statins. So I look at I go into the EMR and I show me everybody who has a statin. All right, and that's the beginning. If you didn't have a statin, you're not part of my study. Then within this study of statin, I now want to look at those who develop neuropathy and compare them to those who didn't develop neuropathy. Something like that. Okay, that's nested case control. Anyway, the authors used a prescription registry to identify exposure to drug, estimated the odds ratio for the use of statin in the case of idiopathic neuropathy compared to controls, and the odds ratio linking idiopathic neuropathy with statin was 3.7. So what does this mean? So what does it mean to talk about the odds of a polyneuropathy and the history of statin use? And how is it different than risk? So odds is a measure of frequency. It is extremely unintuitive. You've heard me say this 100 times. Risk is intuitive, odds is not intuitive. Okay, it's unintuitive because it's a ratio and it's not a proportion. So let's take an example. All right, here we have the exposure. Here we have the disease. They do or they don't. They did or they didn't. Okay, so typical 2x2 table stuff. Here, look, the probability of the disease among the exposed is 20 got the disease among the exposed. So the probability is 80%. Right? Isn't this just obvious? I mean, it jumps out and you go, okay, 80% of the people exposed got the disease. All right. The odds of the disease is the ratio of those who got the disease divided by the ratio of those who didn't get the disease. So this time I do want to write this down on the board for a second, because I think it's important to see this one. This is okay. So A are the people who got the disease, okay, over A plus B. These are the got the disease. No, all right, is B, that's the other group who didn't get it, over A plus B. Now, what I can do is I'm taking the ratio of those who did get the disease, sure, divided by the people who didn't get the disease. So that's A over A plus B over B over A plus B. And this is about the most complicated math we're going to deal with in this course. It cancels, okay? And so we're left with the ratio A over B. And that's it, okay? But you'll see why I put that up here, because I want to distinguish it from something that we get to later. That is the odds. So the odds is those who got the disease divided by those who didn't get the disease within the exposed population. We're not comparing two groups here. This is the point. This is only one group of people, the people who were exposed. And the odds, this is why we're saying it's a ratio and not a proportion. You say, well, there's a division in here too. I know, but this is the proportion of people who got the disease. That's not what this is. This is the ratio of the people who did get the disease over the ratio who didn't get the disease within exactly the same population. Okay, this is very different. Okay, it's very different, and it is not intuitive. So why do we ever do it? If it's such a complex metric, why do we use it? Because in order to use risk, the proportion measurement, you need incidence data, and that's difficult to get. Any one of you right now could start a research project looking at, we can take, Lakshmi's study from today, and she could go into the EMR, and in a week she could begin to define the odds of going blind if you had a stent put in your transverse sinus, right? That would be very easy for her to do. She could do it as a retrospective study, right? But if she wanted to look at the incidence of going blind in people who were stented for idiopathic, intracranial hypertension, it's going to take her 10 years, right? A week versus 10 years. This is a different type of experiment altogether. So you really have to respect people who turn up with risk data. It's a big deal. All right. So when incidence data is not available, and the case control study is a perfect example, then you use odds instead of risk. And later in the course, we'll talk about a second time when you use odds, because it turns out that although risk is more intuitive and simpler for us, the math of logistic regression analysis and things like that becomes almost impossible. I'm not talking about the calculation. I'm talking about the mathematics of deriving the equations. Has never been done. So the logistic regression has never been solved for risk. No one knows what the calculation ought to be. Therefore, when you're going to talk about, which we use regression all the time, you want to control for age, you want to control for gender, you want to control for weight. You can't do that with risk data. You can only do that with odds data. Okay, the math just isn't there. Okay, so all these are measures of frequency within a population, and now we want to look at the ability to compare two populations. So these are measures of association. All right, still at the level of the 2x2 table, same data, same calculation so far. All right, now we're looking at a second group, and these are the people who were not exposed, and we look at the probability, if you will, the risk of their getting the disease. And so the risk in the exposed group was 0.8. The risk in the non-exposed group is 0.4, 80% versus 40%, right? All right. Then we want to compare these two groups. So we can do it two different ways. This is, same as yesterday. We compare it two different ways. We can take the relative risk, or we can calculate an absolute risk difference. They're both valid. There's nothing right or wrong about either of them. They're both perfectly proper, So we're gonna look at an example for both and how they differ from one another. I'll say again, it is not that one is better than the other. I mean it. It's not. Although absolute risk difference is more valuable, because that's what allows you to calculate number needed to treat, which I've already said is, for me, the most important number. So okay, so we'll
medications like
exactly, and Michael will provide us with his favorite example in the next slide probably. So the relative risk, okay, is just the relative risk is 0.8 over 0.4 is equal to 2. And the risk difference is 0.8 minus 0.4. So this is at the additive level. Now, the reason that I put this up on the board, so let's go back to the board for a minute. And you say, well, why is this, here's the question. Is the relative risk the same as odds? So, you know, this is a ratio. That was a ratio. So why are we so keen on this and less keen, if you will, with odds? Because this is not true. This is A over A plus B divided by C over C plus D. These are two different populations. This is the relative risk. Remember, this is a measure of association. Odds was a measure of frequency within a single population. Okay? Relative risk is the ratio of two different populations. Okay? That's maybe the most subtle point of this entire lecture today. All right? So relative risk, this is still very intuitive, right? Dealing with risk is just so natural that you don't need any explanation. So when you want to quantify determinants of disease, we need tools to compare exposure between two populations. The two types of measures are the ratio measures, the relative scale, like that, or the difference measures on an additive scale. Subtraction is after all just addition of a negative number. All right. Michael's favorite is the original Plavix article, the Caprice study from 1996, I believe. And published in Lancet, highly respectable journal, and Michael knew that I lectured about this topic all the time, which is why he used the example. Michael and I have this thing going. At any rate, here's the data that he highlights. Patients treated with clopidogrel had an annual 5.32% risk of ischemic stroke, myocardial infarction, or vascular death, compared with a 5.83 with aspirin. These rates reflect a statistically significant relative risk reduction of 8.7% in favor of clopidogrel. Michael's thing is to point out that the absolute risk reduction is 0.5%. 0.5%. Number needed to treat. So the number needed to treat, how many patients must I treat in order to see one better outcome? That's the question. And the answer is pretty obvious here. So the number needed to treat is 1 over the absolute risk difference. The absolute risk difference is 0.5. The number needed to treat is 200. So you have to treat 200 people with Plavix to prevent one additional stroke. Now, you might say that's worth it. If the risk profile is the same and the cost is the same, well, why not save the 1 in 200? There are 750,000 strokes a year in the United States. That translates into a lot of people, okay? So, but it comes at a cost. And at any rate, what Michael was objecting to here is what Maria was saying, and that is the 8.7% seems substantial. You know, and that's a lot, you know, it's not, okay? Now, we distinguished a minute ago the relative risk ratio from odds. Odds was the frequency in a single population. But sometimes we need to use odds because we have a case control study or something like that. So sometimes we need to compare odds between two populations. So then we take an odds ratio. There's no point in subtracting them, right? We can't do that. Right? Let's be clear about this. We can't subtract one set of odds from another. It's not a linear measure because the odds is already a ratio. So we're screwed. Okay? So you can't do an absolute odds reduction. Okay? It has no meaning at all. So we can only take an odds ratio. And the problem with this is that we're taking a ratio of two ratios. And it gets really nuts, is what happens. And this is what makes it really unintuitive. And I'll show you an example of when it is and when it isn't. So under certain circumstances, the odds ratio provides a close estimate of the risk ratio. So sometimes odds ratio actually works very well. The numbers are very similar to risk ratio, and sometimes they are not. Okay. So here we have a new set. We're back to our 2x2 table. We have different set of data. All right. So here's exposed and unexposed got the disease, didn't get the disease. So 5 of the exposed got the disease, 95 of the exposed did not get the disease, but 2 of the not exposed got the disease and 98 didn't. Same patient population size. So the odds of getting the disease in the exposed population is 5 divided by 95. Okay, so he's done the calculation for us. And the odds of getting the disease in the not exposed population is 2 out of 98. So that calculation, and the odds ratio, which is this number divided by this number, is 2.58. The risk of getting the disease is 5%, obviously, right? You can see that from the data. The risk of not getting the disease, the risk of getting the disease in the not exposed is 2%. So that's pretty obvious also, all right? And the ratio between them is 2.5. So here, odds ratio is a very good estimate of the risk ratio. I'm going to come back to this slide. Let's take a new data set, all right? Exposed, same setup, 2x2 table, but in this case, the exposed people, half the exposed people contracted the disease. Let's do the calculations, all right? The odds ratio of getting the disease if you were exposed is 1. You already go, 1? You know, like 1. My odds is 1, okay? Odds of 1 is a 50-50 chance, but it doesn't mean that, but that's what it is. All right, the odds ratio, we already calculated that once before for 5 out of over 95 is 0.052. And the odds ratio, this number divided by this number, is 19. All right, so this is the odds ratio. The risk of the disease is intuitively 50% if you're exposed, and it's intuitively 5% if you're not exposed, and the risk ratio is intuitively 10, okay? And the odds ratio would overestimate the risk ratio by 2, by a whole, by it would double it. Now it's not wrong, it's not mathematically wrong. It just doesn't work in our head. Okay, that's all I'm saying. It's not intuitive. I get it. If you're 10 times more likely, I get it. Okay, if your odd is 19, I don't get it. I don't know what that means. I really don't. But here's my question now, between these two. What's the difference between these two data sets that makes this, okay, makes this one a good estimate of risk? So odds and the odds ratio is a good estimate of risk ratio. It's a, all right? And in the other one, it's not. What's the difference? Because I want you to know what the difference is, because then you'll know when you can and when you can't trust the odds ratio. Right. And that is exactly the key. In this data, in this particular result, all right, both groups had a low likelihood of getting the disease. And so when the likelihood is low, so when you're looking in the less than 10% range for both exposed and unexposed, then the odds ratio is a good estimate of the risk ratio. And you can feel pretty comfortable. If it says 2.58, you go, yeah, okay, it's about 2.5, and deal with it. But when you start getting up, when you have more than 10%, certainly when you get more than, in either group, more than 20% are getting the disease, then it's not wrong, but odds ratio will no longer be a good predictor of the risk ratio. It's not wrong, it's mathematically correct, it's different. Okay, so we're done, basically. To summarize all this, prevalence describes the amount in a population at a single time. The incidence describes the occurrence of new disease. Rate is incidence over a particular time or amalgamation of people and time. And odds is necessary. It's the only appropriate tool, the only appropriate calculation when you're not dealing with incidence data. And you'll see people make that mistake. And you'll see people talk about risk in a case control study. That is wrong. That's just plain. That is wrong. We talk about valid and invalid. That would be invalid to speak of risk in a case control study. That would not be proper at all. And then you have the risk difference. So with risk, which is incident data, you can either do it by absolute difference or you can do it by relative difference. With odds, you're limited to relative ratio, and that's all that you can. And I would have added, I will add later, that the number needed to treat is calculated from the absolute risk difference. Okay? And that's it. We're done. Good. Yeah. So I don't know what we move on to tomorrow, Monday, but it'll be something. We could see. Let's take a quick look. We have 1 minute. Let's see what's in the module. Module 3 is observational studies. Excellent. Case control and cohort studies. Okay, very good. So that's what we'll talk about on Monday. Very good.
I can take care of it.
Don't close, don't close.
Oh. I think it's Thursday.
Still, we are.